much. We're going to be talking about patching today. My name is Jazz. The VIR is silent or is parity check, depending on how security sensitive you are. I've worked on a variety of small and large tech companies, actually most of them out here in the Bay Area where I'm calling you from. I haven't made it out to Atlanta. You guys should definitely have me out there, all in security all of the time.
Neither did I. I've never been to Atlanta. So I'm Pedro Fortuna. I'm founder and CTO at JScrambler. I do AppSec, and I sometimes do talks, and happy to be here. Let's start this time with a question from me to you, Jazz. Don't you think that organizations are obsessed with patching, like almost if that's all they care about?
It really feels that way, right? Like that the one thing is that they need to be patched fully and everything else in life will be okay. In this talk, I think we're going to talk about why patching, whilst important, is not the panacea, that it is difficult. And one of the things that you can, what else you can do to mitigate the risk of running unpatched software. Before we move on, we wanted to learn about what you guys all think about patching. Before you get influenced by our talk, it's going to be a very influential talk. I'm definitely going to change your mind about all of this. But before that, it would be nice to capture this. If you can hit that QR code, head over to Slido, and put your opinion down. And the question that you have is, assuming you agree that patching is not enough, what other security initiative would be the best to complement it? Now, of course, you are thinking, well, I want to go with all of these, right? But, I'm telling you, you can't. You have to go to this desert island. You're going to be taking patching with you. You're going to probably take a basket of fruits with you. That's mandatory. But you can also choose just one more of these things. And that's it. You have to make a choice. That's just the rules of the game. Strong authentication, isolation mechanisms, attack surface reduction, or vulnerability scans, SAST and DAST. This is dynamic and static. I'm just going to give you like 30 seconds to go through that. If I had some music, this is what I would be playing right now.
Yeah, you can type something on the chat when you're done, just to give us a sense that we can move on.
Oh, that's a good idea.
This is a hard question. Usually when I go to the supermarket, if I hesitate between 2 or 3 things, I'll just take all of them and that's it. But not in this case. You have to choose. All right.
We good?
I don't actually see people like typing in the chat. Maybe I'm not looking in the right place.
I'll give it another 10 seconds. What do you think?
Yep. Maybe we have some configuration problem on Slido. Okay, people are actually saying what their vote was. You don't have to do that. Just say like voted or something.
Yeah.
We don't want you to be haunted by your decision.
Okay, brilliant. Okay, I think that
okay, that's great, people. Like, let's move on.
Okay, so patching is hard, right? Like we all agree, it takes a lot of time to prepare a patch. All the tasks like testing a patch, making sure that it does not break software, that it is functional, that it is performant, and then after you've done all of that, you still need to roll it out. And at that point, you are sometimes dependent on some other team or some other party or sometimes a vendor that you don't control. And now you have to convince them to like roll your patch out. And sometimes after you've done all of that, you've done all of these things, all of the hard work to roll this into production, and you find that the patch does not even succeed at fixing the security vulnerability that you had in place. Just some numbers to help you understand this, right? According to a recent study, there's a link at the bottom there. It takes 215 days on average to patch a vulnerability. So 215 days. The best part of this is that if the vulnerability is critical, it still takes a company at least 6 months, which is 180 odd days, right? Which is still is less than an average time to patch a vulnerability, but it's only 30 days.
It's almost the same amount of time.
Almost exactly. It's almost the same.
It's like the engine only has one speed,
which is slow.
Which is slow, yeah.
I'll
do it tomorrow.
So why isn't the criticality weighing more? Is it because we are lazy or slow? No, we all know that the reality is different from that. But before I come to this, let me tell you why do we end up patching? And every single talk at OWASP and a bunch of other security conferences that have been held recently, I did the same thing that everybody else has been doing, which is I turned to ChatGPT, and this was my attempt. I was like, hey, I don't want to write this talk. Can you just write this talk for me? Can you help me create a talk on why patching is not necessary for security? And even an AI, and you can read the first line, even an AI thought that the premise of my talk was immoral, right? And this makes sense, right? Because what is ChatGPT doing here? It's summarizing the consensus view of the internet. And the consensus view of the internet is that you have to be patched 100% of the time if you are doing anything serious in security. And why do we think this, right? Why do we think that we need to patch? A premise in engineering is that the only way to be secure is if you know what is happening in production. The idea is if your software is unpatched, your software could be doing anything, right? If the attacker gets in, they could be doing a wide variety of things that you do not expect. And as a result, there's no way to secure yourself. The reverse of this, the thing that we extend too far is, if you are fully patched, then your software is fully predictable. If you're fully patched, then you're fully predictable. And the more you think about that, the more you come to realize what a fallacy this is. Now, it remains the case that, of course, if you are unpatched, things may be happening that you do not know, but the reverse is not necessarily true. If you are fully patched, you may still have all kinds of things happening in production that you are not sure about. Now, I'm sure all of you have stories like this. In my case, back at my time at Google, there was this well-known DOM parser called libxerxes or Xerxes, which is an awesome parser for HTML that I was responsible for maintaining within Google. At a large company like Google, I'm sure, as in many of your companies as well, you can only have one version of a library at a time. This is a policy. Now, Xerxes unfortunately fixed a vulnerability, and then at the same version that they fixed a vulnerability, they also removed some functionality that I was relying on in the same version, and I ended up stuck. Do I either choose to race on down and fix the vulnerability, and in the meantime shut down all of the existing applications and let the projects that are reliant on my library to break? Or do I leave them be vulnerable with a vulnerability that I know that we have whilst I am fixing this vulnerability? Now, these are
we all know the answer, right?
Well, you don't actually, because it turned out a very senior person at Google reached out to my manager to help young Jazz prioritize his time to race to fix this, right? And in that particular case, I was a fairly junior engineer. there weren't other critical things that I needed to maintain. And so it was possible for me to reprioritize my time. The point here is that every time we have vulnerabilities, whilst your vulnerability is unpatched, there is a resource balancing act that you are carrying out. It is not the case that fixing a vulnerability has zero cost. And the cost is often that you are choosing to do one thing instead of another. And both of those things may be critical. Even our friends in compliance understand that this is difficult, right? Companies have limited resources. They realize that patches need to be prioritized. What does that mean? If patches need to be prioritized, that means sooner or later, you're going to be running into a case where you have software that is unpatched, that you know is vulnerable. And it's not because you're a bad security engineer. It's not because your organization is neglectful, but because you have limited resources and you have to do a risk-benefit analysis to work out what you can patch and what has to remain unpatched while you race to do testing and organizational deployment and all kinds of other things to get a patch ready to be put into production. This all sounds pretty bleak, right? And so what else can you do about this? What else can you do to make sure that the software that you have running in your organizations remains patched? In order to answer that question, you have to ask yourself, what is the point of patching? And the analogy, this analogy belongs to Pedro. I like this analogy, so I'm definitely stealing it, Pedro. What is the goal of patching? The goal of patching is to really have this beautiful basket of fruit. And the problem that you have is that every once in a while, you have a rotten apple that can spoil the entire basket. And the patching is supposed to eliminate that one rotten apple. But you think about it, if that is an analogy that is accurate, there's a bunch of other things that you can do other than just removing the rotten apple in order to protect your basket of fruit. For one thing, well, it turns out I don't even like apples. I can't stand apples. So there's no point in having them in the basket in the first place, right? This is the attack surface reduction solution, which is if you have resources or if you have software that you don't actually need or don't actually want, you can remove them. Turns out the fruit that you do have can also spoil, and they can spread the contagion to the rest of the basket. What you can do there is compartmentalization. Yes, some of the fruit are going to go bad, but they won't end up spreading the contagion, spreading the spoiling to the entire basket. The concrete example here for attack surface reduction is we have things like SBOM, which has been all the rage at OWASP for a couple of years now. There's this software bill of materials. What does it say? It says, as long as I understand where all of the software that I have is going into my application, I can choose the software that I don't want, or that I don't need, right? As long as I know all of the software that goes into my application, at least I have choices about what it is that I'm doing. We have content security policy for web applications. How are we doing there, Pedro?
Sorry about that. Keep on.
That's all good.
You're doing great.
So I just want, I just want these libraries from these particular locations. That's what CSP allows you to specify. By default, the web allows you to load, all of the libraries from all of the internet into your application. CSP says, no, I don't need that. It says that you can make choices about what parts of the application you don't need imported into your software. And software is not the only way to do this attack surface reduction, right? You can have processes as well. I like to call this CISO with a stick, by narrowing down the type of software or the versions or the particular companies that your company is allowed to use. You can do all kinds of reduction of the attack surface that your web application is vulnerable to. It was a real pain. It was a real pain that for Xerxes, I was limited in the way that I was. But overall, if you think about it, it was really great, right? Because it meant that Google only needed to focus on one version at a time on what kinds of problems, what version of problems it needed to tackle. And that was very much, CISO making sure that the amount of work that a security team needed to do was limited. And the thing that you should have in your head as you think about all of these is, all of these seem like obviously good ideas, but patching was not a necessary part for this kind of attack surface reduction. There's another tool that you can have in your tool chest, and that's isolation. You can make it so that, yes, I'm going to end up being vulnerable, but you can make the blast radius of unpatched software be smaller. So there's many such examples. I have 3 of them here. You have network segmentation, where you don't need to have every node in your infrastructure being able to connect to every other node. Similarly, you can have system-level sandboxing. Yeah, we can use things like seccomp and AppArmor that controls what other applications or what other system resources your app can see and use. And then very close to my heart personally is this idea of virtualization. With virtualization, you can lift an application up and place it, you can replace APIs that the application is using with other ones that do additional things, like do logging or blocking, or sometimes even attenuate the arguments that are being passed to the functions that you're controlling. The thing to remember here is that in all of these cases, you are reducing the blast radius of the attack over the vulnerable software, but you're not necessarily having to immediately patch software.
You can also filter the apples, right?
You can. That's. Thank you. This analogy needs to be pushed a lot more. We can polish these apples. No. But your point stands, right? We can filter parts of an apple. You don't need to choose an entire service or an entire application. You can choose what parts of an application or what parts of a library that you're using are usable or not, and virtualization definitely allows you to do that. There's a couple of practical examples that we're going to go over so that you can properly visualize exactly what it is that we're talking about. As we go through these examples, I would like you to keep at the front and center of your mind, maybe some of the details are there, but the front and center of your mind is, oh, if I had this application in my network, and it had become vulnerable, and I knew about it, is the immediate response that I would need to do is to patch? Sooner or later, you would have to. But is the immediate response that I would need be patching? Or is there other things that I can do to reduce the extent to which I was vulnerable? The first example is network isolation. I'm going to blaze through this because you guys are all, I'm pretty sure, fairly familiar with this. You have a load balancer. It talks to a web server and an API server. Each of these connect to a database. Actually, they connect to 2 different databases. In this particular case, you can see that the load balancer talks to the web server and the API server. The web server happens to only talk to a database, and the API server only needs to talk to a completely separate, a completely isolated, different database, right? By the way, I'm gonna. Yeah, that's right. But I'm keeping an eye on the chat. Matthew mentioned in a perfect world, companies will have unlimited time and unlimited funds. I think that that's actually a better way of capturing the message that we would like to share with you, right? Companies don't have unlimited funds. They don't have unlimited time. And as a result, we do have to make trade-offs. And the trade-offs that we need to make sometimes mean that patching is not possible. In this particular case, the architecture diagrams that you see are exactly this way, that the load balancer only talks to the web server. The web server one only talks to database one. Load balancer talks to API server, and API server talks to only database two. What you will find is, if you ever see the load balancer accessing your database, you know something has gone horribly wrong. Or if you see web server one talking to database two, or vice versa, you know something has gone horribly wrong. Why? You've probably been popped, and probably because you're running unpatched software. The way to fix this is you have to patch your software. There's certainly one way of doing that, and you should. But in the meantime, you can also use network segmentation by enforcing that the load balancer is the only one allowed to talk to the web servers. In fact, you might even be able to say what API calls from the load balancer goes to which API, which web servers, and which web servers, so which web server can talk to which databases, etc. And this is something that you are able to do using IP tables, for example. That does not require you to go ahead and patch each one of these vulnerable pieces of software, but it does mean that the extent to which you are vulnerable to an attacker is now limited. The attacker has to follow the paths that your application normally follows, which dramatically increases the amount of work that the attacker needs to do.
All right.
You want to tackle system isolation?
I do. So our second example is a system level isolation example. And we chose Image Magic library for this example, mostly because it's used by many web apps to automate image edition. And it's also notoriously plagued by vulnerabilities. We specifically picked a command injection vulnerability that was branded as image tragic, which, by the way, don't you think that security people come up with the best name puns?
I think that this is the way that I know that I'm not a real security person, Pedro, is because I have never come up with a name as clever.
Yeah, sometimes I think it's the main reason why they come up with vulnerabilities, just so they get they get to name the vulnerability using some clever pun. So so Image Magic uses external programs to do some chores. These are called delegates, and delegates are basically configured with a template that tells what to do. So in this example, for instance, curl is being used to fetch an image stored at an HTTPS location. But in this case, what they forgot is the basic rule of web application security, that you should never, ever use unsanitized user-controlled inputs in your application. So this is what went wrong. So in this vulnerability, they forgot to do that. And it basically allows someone to inject a command. And the worst thing is that the output of that command is actually returned to the attacker. Okay, so they are able to ask questions and find things about the server that it's running the Image Magic. Okay, so let's see this in action. All right. So what you will see is basically, I'll start with the example that I've just shown you. Get a listing of the current directory. And now let's run Image Magic, and there you go. You can see the outputs. Now you see a secret.txt file. Let's try to look inside to see what it contains. And as you can see, we were able to see inside. Now let's find a more interesting target, say etc password, for instance.
That's a good one.
I'm sorry that you have to see me type very slowly. And here you are. it isn't a big surprise. Let me show you that again. Slower. Okay. And there you are. So we were able to see the contents of that file. So it's very easy to exploit, and it's very powerful for the attacker.
Okay.
So obvious.
Sounds
Yep.
pretty bad.
It is. It's one of the worst. And I would be glad to say it's the only one, but this image magic has a long history of vulnerabilities like this. So, so this vulnerability was quickly patched. Back then, the recommended actions were first, verify that the output, that the images being generated start with the expected bytes, that they look like the image formats you were expecting. Also, you should disable unnecessary delegates. And of course, you should patch. And what are these really? So the first one is do stronger validation. Okay, make sure that the output is legitimate and that it should be returned to the client that made the request. Secondly, attack surface reduction, because if you disable a bunch of delegations that you don't need, you may, in some cases, avoid the problem. And finally, security updates. So what else? What else could we do in this situation? So it turns out that even then, Elkantov published a blog post recommending sandboxing as well. So he really meant seccomp. If you're familiar with seccomp, you need to change the source codes of the application leveraging seccomp. So if you're just using ImageMagick as a third-party software, you probably wouldn't go that far. I know I wouldn't because I'm not in the business of recompiling every software that I use. But there's another option, another sandboxing option on the table. It's AppArmor. If you don't know AppArmor, it's an open source solution based on Linux that allows you to basically block out a Linux executable from accessing files, network, and other capabilities. And then, only then, you have to explicitly re-enable things that the application needs in order to do what it needs to do. So you see a very tiny example in the bottom right where this AppArmor profile is allowing Firefox to use the network and also to have read and write permissions to the directory home/foo. Okay, so this is a very minimalistic AppArmor profile. I'm sure Firefox would not be able to function, but it's just to get you started on this AppArmor profile thingy. Okay, so in this case, what I want to show you is what would happen if, in this case of Image Tragic, people would have used AppArmor to isolate ImageMagick from the system. Okay, and this could be an example of one AppArmor profile to do it. So basically, it's not too difficult to understand what's going on here. So the first line, you specify the full path to the binary running. Then you are enabling the use of the network, some necessarily directories in order to function properly, like access to temp, run, lib proxies. This is very, anyone that knows, is familiar with Linux knows that most programs will need to use these directories. Then, because we have a bunch of delegates, they need access to some configurations placed under etc. Then you have lots of directories that are needed in order to bring the dependencies, the libraries, and all that is being used, and also the bin directory, and last but not least, access to the directory where this executable is running, which is under /my app. And we need read and write permission because we're creating new files. and we also need to read the global directory. Okay, so I don't claim that this is the most hardened AppArmor profile for this example. This is a working example that it's only meant to provide like a easy to follow example so you get the ropes. Okay, I think there's a question here.
Just so that I understand here, Pedro, what you have is still more resources being provided to ImageMagick than it might need to run, but
Exactly.
less than what you would get by default.
Well, way less, way less. You're restricting a lot of things with this AppArmor profile. So Tony is actually asking, why not just run it in a non-root container?
Yeah.
So that could be it. Like you can use containers as a system level isolation. It's perfectly valid. I'm sure you can come up with other examples. I'm showing you a simple way of isolating an executable. You can also use AppArmor inside containers. So you can use all of that in the security in depth approach. Basically, it boils down to how much time you want to invest in doing this, how quickly you can roll this out, how quickly you can solve problems around this if you have them. I actually don't recommend that people write their own AppArmor profiles. There are a few well-vetted AppArmor profiles for known software, like you're running Apache or running something else very common. You will very likely find industry-vetted examples. I would incentivize people, if you want to use AppArmor, you should look for those first, because it takes some debugging time to find like settings that will actually allow the application to run properly without breaking. Because you only know that it's breaking if you are hitting that part of the software that it's requesting some permission that you may or may not have provided through the AppArmor profile. Okay, hopefully I've answered your question, Tony. All right. Okay, so let's move on and see the same exact demo. Let's try to see the contents of etc password, but this time around I will run this AppArmor profile and see what happens. Okay, so the same thing, and as you can see, I'll stop here. We weren't able, like you were not seeing the content of password file, and not only that, but the attempt was logged in the file, and the situation has been flagged, so it can be escalated. Well, assuming that you spend your days combing through your beautiful CM logs, right? I'm sure you are doing that every day, Jazz, right?
Oh, of course.
Okay. So our third and final example is an application isolation example. And for that, we crafted a very small web app. It's basically just a payment page that contains a built-in XSS vulnerability. It allows you to pass an XSS vector using a get parameter, and whatever you put there is reflected to the body. Okay, so it's basically an XSS vulnerability. Okay. All right, so let's exploit this by using a multi-stage XSS payload. The first stage is very simple, just a script source element loading the second stage from baddomain.com, badscript.js. So using a second stage, the benefit for the attacker is that they can change the injected payload at any given point just by replacing the JavaScript hosted under baddomain.com. They might be able to change the stage one, but they don't need to. They can change everything from the stage two. Also, this approach limits the amount of characters being passed to the get parameter, because usually if you have a very long URL, it might stick out in the log files and be caught earlier. So we see this approach all the time. And this would be the second stage. It's very simple. Basically, it adds an onSubmit event handler that when the payment form is submitted, it iterates and collects every field from the payment form, pastes the contents of the form to the console, just as a way to prove that it had access. In real life, they wouldn't do this, of course. And finally, XHRs the data out to a malicious domain, in this case, maliciousAPI.jscramble.com. Now, before I show you this attack playing out successfully, I want to bring up how we're going to mitigate this issue. And for that, we'll be using web page integrity, or WPI, which is a client-side security sandboxing solution that we have been working on for a few years now. It basically allows the application owner the control of what scripts see and do, very much like AppArmor, but for the browser. Okay, so you can enable the things that it will be able to do and be able to accomplish, and everything else will be blocked. And it offers a very expressive rules engine, very granular over a wide variety of code behaviors. So you can think of it as kind of a firewall for code behavior, not user behavior, code behavior. So it's like,
if I'm thinking of it like a non-root container, but for the browser, am I thinking about it right?
It is. It's a sandboxing approach, classical. It uses virtualization, the way you explained it before. So we change the world that each script sees so that we can attenuate and control and filter and be able to mitigate if they suddenly start like showing some undesirable behavior over the page, like accessing a payment form, something like that. Obviously, if you don't trust the scripts, you should consider removing the script from the page. But there are other things that can happen. That script can be vulnerable at some point, and some exploitation of that vulnerability might be able to be leveraged in order to start a new behavior on the page. The scripts can load fourth parties. Fourth parties can be compromised or be evil in the first place. It's such a dynamic environment. Like these days, websites, they use tens of different third parties on the page. So it's also a supply chain issue, which is difficult to control because it can change very fast. And you can do attack surface reduction, which is one of the tools that we have been talking about. You just block out anything that the application will not use, okay? And it allows setting boundaries and isolation rules to prevent any script from touching critical parts of the application. So let's say the payment form is a critical part of the application. Why have all the scripts in that page being able to touch that payment form? You probably have like a well-identified script that actually needs access to that form, and every other script has no business in touching that form. So why not just block that? So we'll do 3 runs. So in this first run, we're doing a no blocking, visibility only baseline, just so you can see the malicious behavior. And during the demo, the bad script.js, which is the second stage JavaScript, will access the payment form and paste the values into the browser console, again, to prove that it could, and then XHR the information out to an attacker-controlled website. So the rule is really simple. You can see the rule at the right. So it's scoped to run in that page, and either a network event triggered by a script source, so loading of so a script element with the source attribute loading a script from anywhere, or a network event triggered by an XHR. Okay, if this happens, you will see an alert. Okay, so let's see it. Okay, so we're running the XSS, of course. So right now, the malicious code, the bad script is already running on the page. This is the dashboard. You can see a request made to baddomain.com on the payment page. And you can see like the script that has been loaded, what was the URL structure, and we haven't blocked anything. So this is only visibility. Let's fill out the form. Don't bother taking screenshots. It's a fake number. I know it's an old joke, but I still have to do it. It's the law. And you can see the data in the on the console, which means that it was able. We have one line here on the drop server. Let me just pause here, and you can see the new item that was successfully sent to the drop server. Okay, so we now have 2 lines here. This is just important because later on you'll see this screen again. You have to memorize how many entries we had here already. Okay, so moving on, there's another alert corresponding to the XHR, and you can see the endpoint where the data is being sent using the XML HTTP request method. And we can see it has not been blocked, and the source of the behavior came from baddomain.com/badscript.js, and it's a form element being accessed in this particular behavior. Okay. All right. So this is the baseline. Now let's move on to number 2. So now we're going to see a new rule that will block any access to the payment form not coming from a well-identified script called processform.js, okay, which is badscript.js is not processform.js. So this rule will totally apply to that. And in this case, the action will be to block, okay? So the same thing again. So we have to fill the form again. Sorry about that. It's the boring part of the demo, hopefully.
It's a different credit card number too.
Yeah, I try to use all of my credit card numbers in demos so people can harvest everything. And as you can see in the bottom, it wasn't able to leak the cardholder data from the page. And let's see, so which means that we were successful in stopping that. We refresh this list, we have no new entries, and here we have 5 new entries. Let me pause here. So we still have the requests via script to baddomain.com because that malicious script is still running. Okay, and it's not being blocked at the moment. And we have 4 other events, each one corresponding to a different form field on that payment form. So we have seen the 4 attempts to access that form. All of them were blocked. Let me show you one of these. They're very similar. Okay. Okay. Okay, so oh, sorry about that. Let me put it back. Okay. So here on the details, you can see what form are we talking about? What is the form name, method, some data about the form, the ID of the inputs, if any, the name, etc. So you can identify what form and form field we're talking about. Okay, and like in similar examples, you can see the script that initiated this this behavior, and some information about the types of data that that field contains, if it's considered to be sensitive data or non-sensitive data. Okay, so for this example, it doesn't matter, like it's a payment form, everything is sensitive, of course. So stage 1 and stage 2 are still being added to the page, so we can improve this. So we can roll out a new rule to forbid the addition of script source elements to the page by any script. So we're basically saying no script should add more scripts in this page. We can say this is a dangerous behavior. I want to prevent any script from engaging in such behavior, so we might as well just forbid this. So attack surface reduction, even if you don't know that this will happen or not, it's still a good idea to be rolling out this type of policies, because of how likely it will be that it will save you someday, even if you don't know ahead of time. Okay, so the rule now is on this same page, any network event triggered by a script source. So a script source is basically like adding a script element with a source attribute. If that happens, we want to forbid that, and the action will be to block. Okay, so a final run. So we already blocked access to the form before, and this time around we want to prevent the second stage from being loaded on the page. If we do that, we are okay. So we made it through. We didn't bother to implement the page after the form is submitted. Yeah, we were too lazy, but don't judge. We were too busy doing other things like I don't know, patching. But let me show you. So you have a new alert here. We still see like the attempts to add the second stage, but in this case you have confirmation that it was successfully blocked. Okay, and I might as well just skip this part forward, because hopefully you got it by now.
So just to summarize here, Pedro, what we are seeing here is WPI and virtualization in general. What we are able to do is prevent the exfiltration of the data in the first stage, and then stop the attack entirely whilst the application was unpatched, right? And whilst presumably the web application developers are racing to develop a patch, but in the meantime, you were able to mitigate, stop, and detect the attack.
Absolutely. Like they might take 215 days to race to get that patch. Hopefully not.
It's a security critical attack, so 6 months.
Exactly. Regardless, that's exactly it. You don't know. You cannot know what will hit your website tomorrow. And when I say website, I could say Linux program or network infrastructure. You don't know. So what we're talking about is not specifically a website. These are just examples. What we're saying is that using surface attack reduction and isolation strategies, or you can generalize this by saying good security architecture. If you use that and patching, you are way better than just relying on you have to patch and you cannot patch fast enough. Okay, so we're getting to the conclusion of our talk. Before we do, I want to take a look at that survey. I don't know exactly how many of you have managed to vote, but let's see this. So, okay, so we had 3 votes, so we cannot gather a lot of conclusions, but it's funny that the one thing that didn't get 1 vote was isolation. So let me go through this. So, and this is my opinion, okay? So it's up to debate, of course. So for me, strong authentication, given the goal here, for me, it's clearly the worst choice. Not that it is a bad thing, it isn't, but it does very little to prevent exploitation, okay? Also, vulnerability scans, SAST and DAST, it's also not the best one, because these approaches, they let you find more vulnerabilities, but they will not catch all of them, especially the hard ones. So if you miss that rotten apple, and using these techniques, you will, because it does not catch everything, the whole basket will still go bad. So I like the attack surface reduction, that it's good because it lowers the likelihood of having a rotten apple, but also it does not eliminate the possibility of exploitation. So definitely, and I would take isolation with me to the desert island, where I would enjoy my mangoes and bananas without any worries in life. I think that's the best bet. Well, come to think about it, why would you take isolation to a desert island? Like isolation is abundant in any desert island. Like that's the definition, right? So I think we got the metaphor wrong, Jazz. We should change it.
100%.
Yeah. But yeah, so for me, it would be isolation. Don't know about you, Jazz. Maybe you want to provide your input here.
So look, part of the motivation for this talk started from a conversation that I had with a CISO that I worked very closely with. And his entire position was that every security decision needed a cost-benefit analysis, except patching. And patching was sacrosanct. You had to patch. And I think that that is a mistake, because there's costs associated with patching. Patching is a critical, important part of the of an organization's security posture. I do not want you to take away from this talk the idea that, oh, I don't need to patch at all. The importance of a clickbaity talk being set aside, patching remains a very important part of what one does as an organization. However, there are alternatives like attack surface reduction, like isolation, that can complement patching and sometimes save us in a way that patching will not. I'm sure you can think of other options than the 3 or 4 that we have covered, but hopefully we have convinced you that these two are highly effective. By leveraging these alternatives, implementing them where they're appropriate, companies can have, I think, a better security posture. We think a better security posture, things like AppArmor, things like WPI, things where what you are doing is removing parts that can hurt you, and then also making it so that the parts that can hurt you have limited amount of impact. These generally improve security posture, and we can be generally, as a community, better prepared against cybersecurity threats. I'll stop here. You're already, what, an hour late to patching your software, right, Pedro?
Yeah, we should let people go, but hopefully they will stay enough to ask a few questions if they have them. If they do not, that's fine. And yeah, so thank you for attending.